Yeah, so today we have three speakers. So the first one is Chih-Cheng Liang from Ethereum Foundation. The second one will be Oscar, and then third speaker will be Sun Shi. So I think the last speaker will be like 5 to 10 minutes. So the first, like the main sessions will be the first two speakers. So we're gonna do one speech, and then discussion, and then the short break, and then Oscar, and then his speech, and then a short discussion, and then Sun Shi. Yeah. So today, Chih-Cheng Liang is one of the founders of Heavy Ethereum Meetup Group, and he joined Ethereum Foundation as a researcher in 2017. And then he's been working on the Hubble project, which is an optimistic rollup with BLS, using the BLS signature. So today he's going to be talking about Polynomial commitment. So welcome.
Thank you, everyone. Thank you, Chih-Cheng, for introduction. And yes, I'm working in a PyZK team in EF. We build zero knowledge proof applications. Although currently I'm working on a project called Hubble project, optimistic rollup. It's using BLS and it's ZK free. It's no movement, only pure EVM. And today we're going to talk about the paper is Chih-Cheng et al. That polynomial commitment scheme. You might heard the names like KZG10 or like Chih-Cheng commitment or vector commitment. They are all referring to the same technique of making polynomial commitments. Why is it it's important? Because it's widely used in SNARKs. In ZK SNARK, polynomial commitment is a very important component that makes zero knowledge proof possible. And the second reason is the polynomial commitment itself is a very efficient commitment scheme. And if you have some idea with blockchain is all about commitments. In the Ethereum block headers, you have rules of you have 32 bytes of post-state root, which is a commitment of like all the accounts and balance and contracts all the data, but all in that 32 bytes. But the blockchain layer 1 or layer 2 scheme you've seen right now, they are all using Merkle trees or variants of Merkle trees and we'll see how the performance compared to the polynomial commitments. So if you're not an English speaker, the commitment might be sounds like a strange word to you, but usually the typical example of business case is like you are a great analyst of stock market, and you are making some predictions of the stock market 3 months later. And if you publish your prediction today, and 3 months later your prediction is correct, and then people blame that no, your prediction is a self-fulfilling prophecy, because if you don't say anything, the smart market will behave another way around. So what can you do as an analyst? When you make predictions, you write down your predictions on a paper, and then you put it in the envelope, and you seal it and put it in the safe. And then 3 months later, you open the envelope and take out your messages, and you can verify if your prediction or match to the stock market. So in this typical example, we can see that the commitment have two steps. The first step is you commit your message to an envelope. So that's let's say there's a piece of data in the blockchain example. It might be like 32 bytes of data, just data. But so and then 3 months later, you need to open you need to reveal your message to the public. You need to show your prediction to the public, and it's indeed the message that's been committed 3 months ago. It didn't change. It didn't get modified. So as we can see, the commitment has two important properties. First, it must be binding. You cannot commit a message and after 3 months the message is different. And the other properties might be important in some use cases, but not all the use cases need the hiding property. So the envelope hides your messages. So nobody can see your message. So your message doesn't affect the stock market if it has the ability to. So binding and hiding. So to understand polynomial commitments, before we look into the hairy math details, we can compare to the Merkle tree. When we do the Merkle tree commitment, the commitment itself is a data of 32 bytes of hash tree root. But if you want to prove a membership of particular leaves is in that tree, you need to provide some data. Usually you call it witness or you call it proof. So let's say if you have a Merkle tree of 32 labeled peaks, and it can hold 2 to the power of 32, which is about 4 billion of leaves. But you want to prove that a certain leaf is in that Merkle tree, you need to provide 32 hashes. There's 32 of 32 bytes, and you can prove to anyone like a server or a blockchain that this leaf is indeed belongs to the tree that committed to the blockchain. So on the other hand, the polynomial commitment, a commitment is elliptic curve element, point element, and it's a G1 element. So it depends on which curve family you are using. If you are using a BM curve, usually we use 128 level of security. It's usually 32 bytes, and BLS 12381 is 48 bytes. We assume that we compress the point. But so the commitment size is similar, but if when opening one, you want to prove the membership of some values belongs to a polynomial, it takes only one G1 element. No matter how big how many numbers in that polynomial it represents. So there are some implications in the blockchain scalability. So here is a hairy math detail, and we want to walk through the flow of proving membership of single values in that polynomial. So that so before we do the rest of things, we need to run a trusted setup. That this is just like the trusted setup you do in the typical zero knowledge proof. So this bracket means we are multiplying 1 to a elliptic curve point in group G1, and this bracket means we are multiplying to the group of G2. so I assume some prerequisite of elliptic curve defining. Sorry about that. So the trusted setup generates a secret value. This is a prime field element. You can think it as a positive integer. So it's s squared, s cubic, and to s power of a very large number. And this secret number is height in the elliptic curve point. So successful trusted setup should generate this. Technically, we call it structure reference string. And no one on earth should know the value of s. They are kept secret to nobody. And so after this preparation, the committer, they have a polynomial to commit. So to produce the commitment data, they compute the polynomial, or they evaluate the polynomial at S and then put it in a G1 group. But as we know, nobody should know the value of S. So this is actually we need a derivation, and then this is equivalent to the coefficients of polynomials multiplied by the structure reference string. So this evaluates to a G1 group element. And then after this value is committed, you want to prove a number that is in this polynomial. So, for example, if we evaluate x at x equal to 1, this equation evaluates to 2. So you want to prove to people, okay, I have a polynomial that is committed on blockchain. It's a data of G1 element, but no one knows what's behind that piece of 48 bytes of data. But you want to prove to people that my polynomial equals 2 if it evaluates on 1. So, but this means if your polynomial evaluates to 2, 1, you can, it actually means that the polynomial minus 2 is equal to 0. And if we think this as a new polynomial, this polynomial must be divisible by the value of x by the polynomial of x minus c. This is usually misquoted as fundamental theorem of algebra, but as Dankra said, it's not. But it's a theorem with no names, but it's maybe for junior high school polynomial textbook. You can actually if it has a if this evaluates to 0 at with a solution x equal to z, so this polynomial must be divisible by x minus z. So we have this quotient. We can get this quotient polynomial, and so actually when opening a point, you are actually you need to prove that your polynomial minus the evaluation is actually to the quotient polynomial times the x on the x point you are evaluating. So you produce a proof like this, and you can compute this value by multiplying the coefficients of Q to the Blocker reference string, like we did before when we compute the commitment. And then you send the verifier. The verifier, they need to verify if your plan is correct. So they take the commitment, and also they take the evaluation Y and to the group 1. And this is the G2 generator. And then they take your proof and they compute this number, this group element. And this group element is actually S2 and minus Z times S. So if this pairing formula equals to each other, then the proof is valid. And why is that the case? Because the pairing formula allows you to evaluate the multiplication, the relation of multiplication. So you can, as you can see, pi is qx evaluated on x, and here is x minus z evaluated on s, and here is y is here, and commitment is px minus evaluated on s. So here is how we do the single proof, and there are some security properties. Is that when you do a commitment, you assume the committer cannot generate another polynomials that can evaluate the same value on S and equals to C. If the committer can do that, that means your commitment scheme is not binding. They can generate another polynomial and evaluate on the same value. So, but it can be proved that it's computationally infeasible. And so, yeah, that's most the technical part I want to talk about there. And what else you can do? So, actually, proving a single membership only takes a constant size of data is already amazing. But hold on to your papers, because if you want to prove multiple points at the same time, imagine if you do it in a Merkle tree. Let's still use the 32 label depth Merkle tree. You prove 1 point, you need to take 32 hashes. If you need to take 10 points, if you prove 10 points, you need to take 10 times of 32 hashes. But if you want to prove 10 points in a polynomial commitment, or maybe a million, you still need a G1 element is all you need. So it's the opening is very cheap in this way. And previously we assumed we commit a polynomial. But what if you have actual data you want to commit? The actual data is usually, if you are designing a blockchain or L2 system, you are having a vector of states, which the state holds your account and balance and like public key or public key ID. This or not this kind of stuff. So let's say you have a vector of values A0, A1, A2, A3, A4. They are called vector because they are older data set. And you can use the Lagrange interpolation to interpolate this data to create a polynomial that represents this data. So this polynomial, when you evaluate 0, you get A0. And if you evaluate 1, you get A1, etc. So this is how you turn the polynomial when you have an actual vector of data, you use the Lagrange interpolation and turn it into a polynomial, and you commit that polynomial and use it to do the rest of the business logic. And yeah, I think that's it. And this presentation is heavily based on the Dankara's amazing blog post. It has more technical detail about the skill.
Yeah, so your presentation was mostly based on Dankara's technical explanation.
Yeah, that's good.
Any questions from people?
So, I want to verify that it's right. That's the right spot. The condition is polynomial was derived from some data. The other thing that we can say, instead of putting the data on the blockchain, we can put the polynomial, so the data is kind of hidden, and no one knows what the data is. And we can verify that this polynomial represents the data.
I think that's possible. I don't know how exactly to do that. I haven't really understand the hiding properties of polynomial commitment, but actually when you send the commitment on chain, you can assume nobody knows the data behind your polynomial.
So the polynomial is always generated from the data.
Yes. Yeah.
Okay.
Yeah.
Yeah. Thanks.
Good question. Yeah.
So also, it seems like one of the main things is like performance compared to Merkle. Are there any differences in terms of security or something?
I think it depends on different set of security assumptions. Merkle 3 depends on the hash function, but and polynomial commitment depends on the elliptic curves assumptions. But there's a question that, okay, if polynomial commitment is that good, why we are not already using polynomial commitment already? Because to construct the proof, so I read there's a paper called Merkle 3. It tried to combine polynomial and polynomial commitment and the Merkle tree together. It makes the Merkle tree has no branches, and it replaces the nodes with polynomial commitment. But it says the polynomial commitment when constructing the proof, you need ONs where with n is the size of your data. And the next lot of application is invisible. Yeah.
Vertical.
Yeah, it's a combination of vector commitment and Merkle tree. Yeah. Yeah.
I'm not very familiar with this background integration. Generate this based on the data.
Yeah.
So I guess the more data we have, is it always possible to generate this 100% of the time?
Yeah, I think. I'm sorry. Yeah, I think it works for any data. Although we assume this data is for a prime field, and actually the Lagrange interpolation is you multiply the data, and this is the Lagrange basis. So, for example, this A1, there it has a term that is the coefficient A1 times its Lagrange basis, which is independent to other bases because its basis it evaluates to 1 at x equal to 1, but the other basis would evaluate to 0 when it evaluates x at 1. Yeah, and so you can think this is we have a bar here. We can pull this A1 to other values to all possible value of A1, but without affecting the other terms. Yeah. This coefficient could be arbitrary without no divisible 0 or
So that means from the side, we store it. So when you don't store it, we have it.
Sorry, I didn't get.
Like the polynomial itself generated.
Yeah.
You just gotta get bigger, the more data you have.
Yes, if you have more data, the polynomial would have more coefficients, but the commitment is still the same size. The commitment is still 148 bytes data, but
There's a commitment since
exactly. Yeah. Exactly.
If the commitment is just simple evaluation to certain point, who stores the polynomial?
So usually, depending on your use case, who is your prover or committer? Yeah, it's often. So
I can say that I have it and I'll show you if you need it. If you okay, let's say if you implement this L1, then your full node stores all the polynomial coefficients and data. But if you are implementing in L2, maybe that's your coordinator, proposer, or something. And if your prover is the user, like the user commits some data on them, then your user store all the. This is possible to allow others to verify this piece of data belongs to this polynomial. How can they verify if they don't have the polynomial?
They don't need to have the polynomial. The verifier only needs the commitment and the proof. So let me show you with this. So these are the information that verifier only needs to have: the commitment and the evaluation. These are sent by the prover, and this you can hardcode in your software. This proof is sent by the user, and this is also you can hardcode. This is sent by the user, but this is hardcode. This is for the structural reference. So yeah.
Is that the it's n squared to calculate the polynomial, right?
I think the n squared is for the Lagrange for the interpolation.
But what's about the variance of the data? You have to recalculate it.
If you update the data.
Yeah, so by the Merkle, if you update a piece, you can just
Yeah, I think so. That's why you need to, when you need to update the data, you need to compute the whole entire data set. So that's why it's costly to
Yeah, thanks Casey for this presentation. I'd like to thank Taipei Hackerspace Temple. He provided this space and 谢谢你从南港特别赶过来开的。So we'll take a short break and we'll off the room.